theorem. Okay, what is this Helmholtz theorem? Okay, actually we have discussed about the basic Maxwell's equations. After basic Maxwell's equations, we have discussed about scalar potential and vector potential. Okay, what is the scalar potential? The scalar potential is the scalar potential is the potential surrounding the static charge particles. Okay, if there is a charge particle, static charge particle, the potential surrounding the charge particles is a scalar potential. If the charge particle is a dynamic charge particle, then the potential surrounding that charge particle is a vector magnetic potential, or simply you can say vector potential. Okay, in our last class, we have derived the relationship between this vector potential, scalar potential, and electric field and magnetic field. Electric field means electric field intensity, and magnetic field intensity. What is the expression? E bar is equal to minus of gradient of V minus dou A bar by dou T. We have seen, right? Those are the expressions. Okay, we have solved those equations. Simply we have substituted and solved those equations. We have come to the two different equations. We have arrived at the two different equations. Okay, they are called, these are the wave equations. Okay, in differential form. These are the wave equations in differential form. They are also called coupled equations. Okay, these equations we can convert this equation to frequency domain also. How we are converting this equation to frequency domain? Simply replacing dou by dou T is equal to j omega. Okay, by replacing this dou by dou T, dou by dou T with j omega, we are arriving these equations. Okay, in our last class we have seen how to derive these equations. Now, have you discussed this Helmholtz equations in our last class? Dear
Yes, sir.
students, we have discussed it, right?
Yes, sir.
The frequency
Yes, sir.
domain representation of these equations. Okay, very easy. You have to practice these equations. Okay, how you are substituting that identities and Maxwell's equations. Okay, here we have discussed this so far, right? This also I have discussed. Okay, these are the representation of this wave equations. Okay, in time domain and frequency domain. Okay, now let us consider we are having a current carrying conductor. Okay, here it is a current carrying conductor. Okay, and the current passing through this conductor is I. Let us assume for our examination purpose, we are assuming a differential small volume. Okay, let us say the volume of this small um, area, the small volume, let us say this is dV. Okay, now we are observing, okay, we want to observe the scalar potential and vector potential at this point P. Okay, let us say in a spherical coordinate system, we are assuming that this is the origin and this is the unit vector in this direction and this is the unit vector in this direction. Okay, let us assume the distance between the observation point and the differential volume is small r. Okay, here, okay, the scalar potential and the vector potential is a function of, okay, see here, based on the r also, the scalar potential and vector potential also will change. Here we can say that the scalar potential and vector potential is the function of r and t. What is r? The distance. What is the t? Time. Why? Because here the electromagnetic waves, okay, they are traveling from source to the destination. They are traveling r distance. Therefore, okay, because of this, okay, we can say that, okay, the scalar potential, vector potential are function of both t and time, t and small r distance. Therefore, we can write the vector potential at point P from the source, the distance from the source is r. We can write a of r comma theta is equal to volume integral mu into j bar divided by 4 pi r. What is j bar? J bar is the conduction current density. Similarly, the scalar electric field or electric field potential, or simply you can say scalar potential or scalar electric potential, you can say this also, no problem. Scalar electric field potential at point P is given by, we already know this equation, this volume integral rho v. This is the charge. Why is this charge? If the current is passing through to this conductor, there is some charge will be there in this differential volume. That charge volume, that is the volume charge density for that region is rho v. Okay. Therefore, the scalar potential also we can write as volume integral rho v by 4 pi epsilon r into dv. Epsilon here is the permittivity. Okay, mu here is the permeability. Okay, this is valid if the current source is a constant current source. If it is not a time varying current source, then these equations are valid. Okay, my dear students, here from here onwards I want your undivided attention. Why? Because a little bit of mathematics are involved. Okay, our time also they reduce 20 minutes. Okay, that's why, okay, you have to be little careful to understand these concepts. For a constant current source, here the current which is passing through this conductor is a constant current. Okay, there is no change in the current. Therefore, okay, these are the equations, okay, we have to use. But in our real case, okay, but in practical case, okay, here the current is not a constant current, it is a alternate current passing through the conductor. What do you mean by that? Because of this alternate current, okay, all the alternate current, how the alternate current look like? How this alternate current will okay, how this alternate current will look like? Okay, it's like this, right? Okay, because it is the current is 0 here and it will come to here. Let us say it is the maximum, I maximum, and this is 0. Again, it is minus I maximum, like this. Okay, because of the change in the current, normally, okay, what is the direction of, suppose we have placed a conductor in the z direction. Okay, okay, what is the direction of magnetic field? Can anybody tell me what is the direction of magnetic field? Hello. If the current carrying conductor is placed in a z direction, what is the direction of magnetic field? Hello. Hello. Dear students.
XY plane, sir.
Not okay, not XY plane. Okay. What is the direction? Magnetic field direction.
90 degrees perpendicular to current, sir. Electric current.
Okay, it is perpendicular to electric current. See, we can use the right hand thumb rule. Okay, if the current is passing through the in this thumb direction, okay, the magnetic field will be like this. Magnetic field will be like this. See, if the current is passing in this direction, the magnetic field will be like this. Okay, what is the direction here? This is the direction. If the current increases, the magnetic field strength also will increase. Okay, like this. Okay, if the current increases further, this also will increase. Okay, this is surrounding like this. Okay, what happened to the electric field? What is the direction of the electric field? What is the direction of the electric field? Okay, the direction of the electric field will be like this. Okay, if you increase the current, okay, if you increase the current, the electric field also will increase like this. Okay, it will increase like this. Okay, if you decrease the if you decrease the current, let us say here, see, which is 0 and constant increasing, and after that it will decreasing. Okay, if you decrease the current, the magnetic field also will decrease and the electric field also will decrease. Okay, you see here, another half cycle, it is negative value. Negative value means if the direction of the current will be changed. Okay, direction of current will be like this. Okay, if the direction of the current changes, what happened to the direction of this magnetic field? Now the magnetic field is like this. Okay, the current is the magnetic field is like this. Like this means, okay, how it will look like? The magnetic field lines are like this. Okay, the direction is in this direction. If you increase further the current, the magnetic field also will increase. Okay, what happened to this electric field? What happened to this electric field? The current is coming this side. Okay, the magnetic field lines are like this. Okay, if you increase in the negative direction, okay, it will increase like this. This is the direction of the electric field if the current is passing in this direction. Okay, therefore we can say that if the changing in the current, okay, causes the changing in magnetic field and electric field. If the direction changes, the direction of the magnetic field also changing and the direction of the electric field also changing. Okay, therefore we can say that the time varying current passing through this conductor produces, okay, different vector potential and scalar potentials. They are also varying with respect to time. Okay, you have to understand this. Okay, okay. Please see here. Okay, these are the for constant current source. Okay, for the constant current source, the vector potential and the scalar potentials are, we can write like this. Okay, for time changing, for time varying fields, that is the AC current passing through this conductor, the electric field and magnetic field also changes with respect to time. The fields will vary with respect to time. Okay, as the current increases, the electric field and magnetic field also will increase. If the current decreases, the electric field and magnetic field also decreases. If the direction of the current is changed, the direction of this magnetic field and electric field also will change automatically. Therefore, there is a finite propagation time is required to travel, okay, to travel the wave from source to the observation point. Okay, therefore, see, for time varying current, okay, the the electromagnetic waves, okay, they require some time to travel from the source to the observation point. The time is called the delay time, propagation delay. How can you represent the propagation delay? This is nothing but the distance divided by the velocity. What is the velocity of electromagnetic waves? The velocity of the electromagnetic waves is, okay, light velocity. Therefore, the time required to travel this electromagnetic waves from source, this is the source, to the destination is rho by v. Okay, normally, okay, these waves are delayed by r by v times, r by v times. That means, see here, suppose if the current is passing through, let us assume here also a small infinitesimal small differential volume dv. Okay, and the volume charge density rho v. Okay, let us say the time required to travel the current, the entry time into this differential volume is t dash, and the exit time of this differential volume is at small t. Okay, the relationship between t minus t dash minus t is given by, see here, the relationship between t minus t dash. Let us say this, to take this one, this side, Okay, this is T minus, you can write. You can write in this equation also. You can write in this equation also T minus T dash is equal to R divided by V. This is the equation. T minus T dash is equal to R by, you can write like this also. Okay, because see here what is the R? R is the distance from the observation to the source. What is the V? V is the velocity of electromagnetic waves. Okay. See, for time varying fields, that is the AC current passing through this conductor, the electric field and magnetic field changes with respect to time. The fields will vary with respect to time. As current increases, electric field increases and magnetic field also increases. There is a finite propagation time is required for wave to travel from source to the observation point. Finite propagation time is required. That time required to travel is called propagation delay. Okay, we can say the time required is T minus T dash is equal to R by V. Okay, see here, because of the time varying current, the scalar potential and vector potential also, they are also retarded means there is some delay, because see the conduction current density at T dash is due to the, okay, see here the vector and scalar potential at T dash at T, the vector and scalar potential at T is responsible, okay, for the conduction current density at T dash. Okay, T dash is delayed actually, but because of the T dash at time T, we can able to measure that vector potential, scalar potential at P. Okay, the effect of the conduction current density at T dash will result here at this point. Okay, the time is at capital T. Okay, in other words, we can say that there is a propagation delay, okay, of the electromagnetic waves. They travel from source, this is the source, to the destination. Okay, therefore you can mention this vector potential and scalar potential as function of r distance, comma T minus R by V. Okay, here, are you able to hear my voice? My voice is clear? Hello, dear students. My, my voice is clear. Is it audible?
Yes, yes.
Okay. Are you understanding this concept? Because of the time varying current, these scalar potential and vector potential also, they are delayed. Delayed means here the time T is equal T, you can write T minus R by V. Okay, see in these equations, simply replace in place of T, okay, T dash is equal to T minus R by V. See here, I mentioned here the vector magnetic potential A at a distance R at a time T due to the current density J at time T minus R by V, that is T dash. Okay, that is T dash. Okay, the conduction current density at a T dash will result the magnetic potential at a distance R at a time T. Okay, that thing you have to understand. Okay, therefore, the vector magnetic potential A for time varying fields is in that above equation, you have to replace T with T minus R by V. Therefore, in this is the expression. This is the expression for the vector potential at a distance r from the source.